Hello everyone, this is our electric aircraft design project. Going forward, power distribution will be taught by Daniel, simulation will be taught by Satya, motor drives will be taught by Paul, converters will be discussed by Nursultan, battery design for non-electric aircraft will be discussed by Musaid, wire selection and characteristics will be discussed by Munir, safety consideration for electrical systems will be discussed by Harshita, high voltage challenge will be discussed by Kevin, and resilience of the system will be discussed by Cyril. Shown to the right is our electrical schematic of our power distribution with 4 different voltage lines. Each line will support various loads in our aircraft and were derived from component constraints. We first started with our motor and reverse engineered the battery sizing and power output. To better optimize this system, we needed a better battery energy density, but also more efficient converters with better switching properties.
To study the overall behavior of the aircraft during the flight, we have created a model with Simulink, which simulates the main components of the aircraft. Here, for instance, we have the battery. Here we have a boost converter. In a motor block, we have a controller, an inverter, a synchronous motor. And thanks to this simulation, we can have some results such as the state of charge of the battery during the flight, or we can study the motor speed and compare it to the reference.
2 is the motor's parameters of our choice, so we use space vector PWM for generating the operation voltage and current control. The result on the right-hand side shows that it can produce the maximum operation voltage to the motor, and the current is quite stable. However, when we look at the aspect of the motor speed, we can see that the motor is oscillating because of the inertia and the low torque distribution. In order to stabilize the motor speed, we use a PI controller for closed-loop control, and this is the gain we designed. As a result, although the low torque change, the speed remains at 228 radians per second.
For this part, I designed a 2 DC-DC converter. First, full bridge converter. It's for 2 transmissions. Second, buck converter. It's for lights, charging port, controller source, and so on, with 28 voltage output. I did simulation part on Plex program. All circuits work properly. There are converters design parameters, constraints, and simulation parts.
Since the aircraft is expected to be in service in 2040, battery technologies which are still under development were considered as a potential option. Using Excel, we were able to calculate and obtain the results shown in the tables at the top right corner. After that, using Simulink, we tested the performance of each battery technology and obtained the graphs on the left, which represent the state of charge during climb and cruise. Finally, we compare the overall results as shown in the table at the bottom of the slide. In addition, thermal methodology indication, BMS, the mathematical equations, and the rationale behind our selections are all discussed in detail in the report.
Wiring is like a nervous system of an aircraft that is designed to bear consist electric current and used to operate the motors, navigation, radios, and transponders as well. We have some specific criteria to make a wire selection such as the flux density, skin effect, AWG, and the most important of the terminal, along with the insulator. We are using the shielded and coaxial cables according to different applications and safety requirements.
Here we are discussing the safety considerations to prevent potential failures and damages and also protect the electrical architecture of the aircraft. Some of the main failures that are taken care of are short circuits, overloads, series and parallel arcs, faulty operation, skin effect, etc. A set of protection components that are employed to taken care of wires and circuits from overload conditions are fuse, magnetic circuit breakers, relay, residual circuit breakers, and etc.
Some high voltage issues we might face are arc faults and partial discharge. They tend to erode installations of the interconnection systems and cause overheating of the wires and damage the electrical equipment, which is dangerous to the safety of the aircraft. Recent research has suggested using deep learning methods, particularly convolutional neural networks, to detect subtle voltage fluctuations that might be a result of partial discharge or arc faults. The algorithm will then trigger a remote control circuit breaker if such faults are found. However, these faults are usually mitigated by frequent safety inspections and proper maintenance.
My name is Cyril. I'm going to be talking about the overall resiliency of our system. We're able to make a system fault tolerant by the use of key redundancies at critical system components, thereby increasing the overall reliability. And we're able to prevent critical faults from cascading through the network through the use of a containerized approach for a subsystem where circuit breakers and disconnect switches covered certain components so that in the event of a fault, they could be islanded and the fault prevents it from cascading. And then in addition, system monitoring allows us to detect faults early and address them before they spread.